Okay, welcome back. So today we will continue our discussion on deep learning, right? And in remember last class we looked at CNNs or convolutional neural networks, right? In fair amount of detail. Um, and today's we will look at another polar sort of architecture called recurrent neural networks, right? And very broadly, right, the CNNs, the primary operation is convolution, and originally they were proposed for uh, you know data from vision or image domains, right? On the RNNs, the the key sort of operation is recurrence, and typically, right, the original models were thought of in context of NLP, right? So this was sort of a typical usage, but as I've described earlier, right, they have also been used in sort of combination where you require to work with images as well as text. Okay, so let me sort of redraw the uh, diagram that we had looked at few classes back. Is about recurrent neural networks. I'm just looking at my notes here, right? So remember, the key idea in recurrent neural networks was to follow through this hidden state computation in time, right? So I'm drawing here various hidden states at various points of time. And so suppose this is at time t, and what happens is that you give it input at time t. Let's call it xt, and this is the forward direction hidden computation, which gives you h h f t. Okay, and this is sort of the backward direction computation, which essentially is given h backward t. Okay, and each of these units is given the corresponding input, the backward direction as well as the forward direction. Okay, and then it outputs, uh, right? So in fact, even before it outputs, there is a small network here sitting here, which takes this entire hidden representation, which is h f t and h b t, right, sort of composed together, and it passes it through another, uh, you can think of it as a neural network or set of layers. In the simplest case, it can be simply a perceptron, right? And that, right, it outputs y t hat, where the y t hat is given by t, which is our non-linearity function, which could be sigmoid, into, let's say, let me call it w o, right, which is sort of the weight of the output in this box, output box, transpose um, h t f h b. Let me make it precise. H t back plus b o. Right, so this is my output, and at each point of time, also let us look at how these hidden states are being computed. We will have h t plus 1 forward direction will be equal to g of w t, uh, and because these are the weights in the forward direction, let me call it WF. Make it clear. So this will be W forward transpose into H T F X plus the bias term, right? So this is my hidden vector computation in the forward direction. This should have been xt here, and similarly in the backward direction we will compute ht plus 1 backward. This will be g of w uh, b transpose into h. This will be t plus 2 because we are coming from the backward direction, so this will be ht plus 2 backward xt plus 2 plus well xt, right? This is simply xt plus b. This will be forward and this will be backward, right? So this is my computation in the backward direction. Actually, let me make it consistent here. In fact, let me correct it this slightly. So this will be hbt minus 1 and this will simply be hbt. uh, right? So this is what we'll get, right? So going forward, we will have hf t plus 1 depending on ht in the forward direction, and backward because we are going backward, ht minus 1 will in fact depend on ht. So now this is one kind of architecture, and I must say that variations have been proposed on this architecture. For example, what people have done, right? In fact, this is this architecture that I just showed here is described in the deep learning book, uh, which I guess it is by Joshua Bengio and other authors. I will post a link on the website, and if you look at section 10.2 there, then this describes this basic neural recurrent neural architecture. I think the notation there may be different, but this is basically the architecture that they describe in this section. I must say that variations have been proposed. In fact, I'm going to describe one idea that is really has advanced the field quite a bit, which is about the attention, uh, which builds on top of this. But before we go there, I want to mention another variation of this, in which instead of outputting uh, the hidden representation at every time step, what is typically done is that you, instead of doing this at instead of feeding the forward and the backward hidden states, what you do is you compute a final context vector, right, which you will refer to as cf uh, in the forward direction and c backward in the backward direction, and this is sort of your final context vector, right? For example, going forward, uh, the last time step, right, whatever state that you get at the last time step, that is uh, h t forward, right? This should have been the superscripts, right? So this is cf and this is cb, right? So similarly, cb is nothing but h backward at time t, or at 0, right? Because in the beginning, right? So these are sort of the final context vectors which are computed, and instead of feeding in hft and hbt, right, you can also feed in, instead of this arrow, you can give these context vectors, which are the context vector cf and cb, right? So there is a common context vector, and think of these context vectors as capturing the final hidden state after time steps, t time steps, right? So in the forward direction, it will be the final time step uh, hidden state, and in the backward direction, it will again be sort of in the backward direction the final context that you capture. And instead of giving the hidden state at every time step, you can also give this context vector. So this is sort of one variation that has been proposed, and the idea of attention sort of builds on that this context vector uh, CF and CB, which I'll describe in the next slide. Okay, so let me draw the picture again. Um, and I'll simplify a little bit just to not to clutter the notation. So assume that these are sort of your hidden states, and I'm just representing hidden states in one direction, right? Just to keep the notation simple, but it's exactly the same idea in both. If you take both forward and the backward direction, in fact, you will see that the forward and the backward direction may not even be required in the case when we are dealing with what is referred to as attention, right? So these are my hidden states, and let's say there is a hidden state at time t, at which takes input ht and outputs ht. Okay, and remember the y's were being produced by taking either this ht as input, or the way I described in the last slide, taking the context, right, which is sort of the last hidden state representation, right? So c is nothing but h uh, t, capital T, right? And as I said, we to simplify the notation, let us say that we are only flowing information in one direction, and we'll see why this makes sense very soon in the idea of attention, right? So C is the final sort of context, and based on this context, what you output is yt hat, right, which is your prediction at time step. In fact, what is typically done is there is also uh, the this output box here can also be sort of constructed by in the form of a recurrent neural network, where to produce output yt hat, you not only take the context c, um, but also maintain a hidden state representation for the outputs. Let me call let me donate them uh, let me denote them by q, right? Uh, so this is q, uh, right? Rather, this outputs q t minus 1, and this outputs q t, right? So these q t's are hidden state representations for the output, right? So the sequence, output sequence, is being produced in the order y1 hat, y2 hat, and up to yt hat, and so on, right? And since we are producing this in the forward direction, think of this, for example, uh, in the part of speech tags, right? So we are sort of processing the sentence and outputting these. So when you are outputting yt hat, you have all the information of what has been produced till now, and that may be useful, and which is being captured by this qt minus 1 um, hidden state representations. uh, okay, uh, clean the slide a little bit. Uh, okay, then in our notation, yt hat will be a linear sort of combination, or a matrix w output, which is the same notation as before, and this is multiplied with whatever input you're getting, which is qt minus 1, and c plus b0, and then you take g of this, which is you pass it through the activation function, and this becomes your yt hat, right? So what have we done from what we described in the previous slide? Instead of outputting h t minus 1 at to produce the output. We have accumulated the entire context C um, till the end of the input, and we are giving this context C to each uh, for producing the output at every time step t. And also we are maintaining a hidden state in form of qt minus 1, qt plus 1, and the last hidden state, output hidden state, is being also fed to produce the output yt hat. There's a little bit of detail here, which I will just describe but not really write on the slide, which is often you may also want to feed in the previous output itself, which is yt minus 1 hat, into this unit computing yt hat as an additional sort of input. But let's not sort of confuse or clutter the notation more. I think this is sufficient for our purpose. And building on this idea, the idea of attention, right, which is a very famous paper by um, Baha Danau, I hope the spelling is correct, a paper from 2014, which originally proposed this idea of attention, um, and which got really popularized. uh, was It was proposed in the context of sequence to sequence architectures. Was the idea that instead of giving the context C, which is a sort of global uh, for producing the output at every time step t, you instead make it ct, right, which essentially means that it will depend at a particular time t, and we will see that ct essentially gives different weights to different hidden states, uh, um, depending on where you are in your sort of output, right? So let me just describe this ct competition in a bit. In fact, not to clutter this slide too much, I let me take you to the next slide, where I'll sort of redraw some of these things and also describe this city competition. But before that, I think I should mention that this paper I'll post on the website, and it has all the details of this attention competition. Okay, so let me describe the idea of attention on this slide, right? So these are my hidden states in time, right? Let's say this is xt being fed in, and this uh, produces ht here at this time point of time, and this is in the forward direction, the computation of the hidden state over the inputs, and somewhere here sitting on the top of the slide is these output hidden states. um, right, let me sort of redraw them just to sort of align them with the corresponding inputs, right? So I will draw it here, and one here, one here, and right, and at time t the output that we produce is yt hat, and there is also a sequence of hidden states that is being maintained now, which is denoted by this q, qt minus 1 and qt, and so on, and at different time steps we produce the output yt plus 1 hat, and so on and so forth, right? And remember that we are also giving this the context vector c, which is being used to produce the output yt hat, right? So now the idea in attention is that instead of giving the context the same context c at every point of time, right, can we replace this by something which is time dependent, or which is ct, right? And how do we really compute this ct? The key idea is to draw this box, which you can think of as the attention box, right? Which sort of takes uh, inputs from all these h1, h2, and so on, right? ht, right? So it takes input from all the input hidden states, uh, and this is the last time step ht, right? It takes input um, from all these input hidden states at various time steps, and it also takes input the current output hidden state, which is qt minus 1, and produces a set of scores, a set of normalized scores, which is denoted by alpha uh, t, right? So because this is the time t, so this is alpha t1, alpha t2, and up to alpha t uh, capital T, right? And here the capital, the subscript denotes the time at which these alphas are being computed, and the superscripts 1, 2, 3 up to capital T denote the weight of the corresponding uh, input hidden in particular, it is not very difficult to see is that this CT will be a weighted combination of these HTs at various, or HT primes at various time steps, and the weight of each of these HT primes will be alpha T and the superscript time T prime, and sum over all possible T primes going from 1 to T, right? And this is my ct, and when I go to compute yt hat, this will be as earlier. So we will have a w sort of output, and this now will be given the uh, this now will be given um, not only q t minus 1, but also c t, uh, right, which is the context at time t, which is in some sense a weighted combination of these ht primes plus b o, and then as before, this is passed through the activation to produce the final output yt hat, right? So this is the key idea, and um, and maybe on the next slide I will describe how to compute these attention weights alpha t 1 up to time step capital, or rather for each of these input hidden states, and note that at every time step t, which for which output yt hat is being produced, we will compute different alpha 1 alpha, these different alpha t's, and they will depend on the current state of the output, essentially. And finally, let me describe this idea of computing these alpha 1 to alpha t, 1 to alpha t up to t, right? So let me just draw the boxes again here, right? So these are our hidden boxes, right, in the input or corresponding to the input layer, right? And this was our attention box that we had drawn earlier, right? This attention box takes input from all these hidden representations at various time steps in the input layer, and it also takes the hidden current hidden state of the output, which is qt minus 1, and produces these alpha scores, which are computed as follows. First, we compute the scores, which is A, T, T prime. Think of these as normalized scores, and these are computed by um, let's say, a single perceptron, which could also be a sort of a general neural network, right? So these take the weight W, weight matrix W attention, and it is multiplied by qt minus 1, and we have h t prime, which is the hidden computation hidden state at time t prime in the input, plus b, which is the bias term, right? And then take the sigmoid or activation of this. So this computes the weight, unnormalized weight, right? So you can think of these as unnormalized scores for the hidden state at time t prime, and all these weights all the scores or weights are being computed for computing the output yt hat at time t. Okay, and then finally, the way we normalize this is using what is referred to as softmax function, um, which gives us the final scores alpha t, t prime, and this is a generalization of the logistic function that we have seen earlier in the case of logistic regression, uh, and this is given by a e or exponential of a t prime t divided by sum over all possible t primes e to the a t t prime, right? So this is the generalization of the logistic function, and to see that, if you take the numerator and divide uh, every term in the denominator, then you will get 1 over 1 plus e to uh, a bunch of terms, 1 over 1 plus bunch of terms, each of which is of the form e to some linear combination of these unnormalized scores ATs, right? And it is not very difficult to see that this is exactly of the form 1 over 1 plus e to the theta transpose x, that is 1 over 1 plus e to the some linear combination of inputs in the case when we have only two classes or two time steps t prime, which is 1 and 2, right? And this is sort of homework for you to go back and essentially read about this and figure out the connection between softmax and logistic. And finally, let me write this in a different color. Right, this entire computation is then used to compute the context scores CT, which is nothing but CT is alpha T E prime into H T prime sum over all possible T primes, right? And this was then finally used to compute YT times as was described on the previous YT hat as is described on the previous slide, right? Okay, so I think um, uh, Uh, right. So I think before we proceed on to the next slide, let me just describe, some of the key ideas here. That this idea of attention, I've described this earlier, is mentioned or was first introduced in the form that I've described here was by paper by Padano et al. 2014. And please read the relevant section. I think it's section 2 and 3 from that paper. To get more clarity on this, there may be slight difference in notation, but the idea is pretty much what I've described here. And secondly, this idea has later been generalized to what is referred to as self-attention, and also something called the transformer architecture, which have become fairly popular in the literature. And in fact, they have been shown to sort of completely get rid of these recurrent connections by using attention on of the input on the input itself, right? And this is a slightly more advanced topic, and maybe I will not go in more detail here, but I'll encourage those of you who are interested to search online, right, to look at the relevant paper on transformer architecture, and go through the details there, right? So once again, right, what have we done here is we have described the whole sort of recurrent computation for what is referred to as sequence to sequence architectures, and note that whatever we have described here uh, um, right applies. We have done it in the context. We have done it in the context of right when there is a one-to-one correspondence between the output and input, but it easily generalizes, especially this idea of attention. It easily generalizes to the case when you have different number of tokens in the input and the output. But the key thing or key takeaway from this attention idea is that right, based on what the current output needs to be produced based on the current input, current hidden representation, qt minus 1 of the output, right? You may want to weigh different hidden states, right? A hidden state of the input at different times differently, and which is captured by these weights alpha t1 up to alpha t, and this gives you pretty good results for many of the applications. Right, so this is what I want to say about RNNs and attention. And now let me move forward to the next subtopic, which is about generative adversarial. I also want to mention before we go to GANs that I'll be posting relevant paper links on the course website. These include the original attention paper, which was proposed in the context of machine translation by Baha Danau et al. In 2014. Transformer architecture, which also proposes the idea of self-attention by Baswani et al. 2017 from Google, and any other relevant papers. Okay, so let us move on to GANs, or generative adversarial networks, right? And recall that we had looked at the basic architecture of these GANs, which play a sort of an adversarial game where there is a generator network G, right, which takes as input a random vector, right, and produces an output which is referred to as Z, and feeds it this Z into a discriminator network, right, whose goal is to essentially discriminate between these Z's produced by the generator network and X's which are being sampled from some underlying set of data points, and the goal of the discriminator is to assign, right, it's like a classifier, right, whose goal is to assign a probability to each of its inputs, uh, and the whole idea in this adversarial sort of setting is that if the input is d of x, then we would want it to be more than, let's say, 0.5, rather close to 1, and if it is dz, which is the output of the generator, then we want it to be less than 0.5, right? Right, and of course the discriminator does not know where the data is coming from, right? Just looking at its input, it has to figure this out, right? And if the discriminator can do this job well, then it can give a feedback to the generator saying that it is able to separate or distinguish the points generated by the generator from the data, and this feedback is in turn taken by the generator to really change its internal sort of weights, so that it can produce better samples, or samples which look more like those coming from the original distribution. And the whole idea is that they sort of improve each other in turn, and finally when the training ends, then dx uh, and dz both are close to zero point 0.5, right? Which means that discriminator is now failing, right? It is not able to discriminate between x and z, and which essentially means that generator is able to generate points which are pretty much look similar to x, right? So this was the basic idea of these GANs, and now let me go in a little bit of more detail of how these are trained. Right. So for that, let me describe this generator by a set of parameters which are theta, and let me describe this discriminator by a set of parameters which are referred to phi. Right. And our goal here would be to define a loss function which would be expressed as L theta phi, right? And this loss is what we would try to minimize as we train both the generator and the discriminator. But before we go there, let me describe an important idea which is essentially uh, prevalent in almost all of deep learning, is the idea of cross entropy or cross entropy loss, which is again used in the context of these GANs architecture. So how do we define cross entropy? Given two random variables x1 and x2, the cross entropy between x1 and x2, cross entropy between these random variables x1 and x2, right, which may have their own distributions, uh, p1 and p2, is essentially defined as uh, minus p of and note and they are defined over the same sample space, right? So they are defined over the same sample space, right? And but they have different distributions, and the cross entropy between these two random variables is simply minus p of x1 equal to x log of p of x2 equal to x, and then sum over all possible x's, right? And note that this entire expression reduces to entropy uh, function when x1 and x are have the same distribution, right? Um, and it can be proved that suppose I fix the distribution of variable x1, and if I vary the distribution of variable x2, then um, cross entropy between x1 and x2 is minimized when x2 has uh, distribution identical to x1, right? So in some sense, when we are trying um, to optimize over distribution of x2 to be same as distribution of x1, and we will see an application of this in the cross entropy loss. Then cross entropy can be good function because it is minimized exactly when the distribution of this variable x2 becomes identical to distribution of variable. And this idea is described in the following, right? When we say L cross entropy uh, loss, right? So think of a classification problem which has L labels or R labels, right? So the label space, right? Y belongs to, let's say, 1 to R, and we have a predictor or a model, right, which gives a probability of PL to the output label L, right? Then we could compute the cross entropy between the actual data labels, right? The probability of getting a particular label L is simply you know um, in the data is simply the indicator function, because right, I mean, it's a sort of a um, it's a 0 1 distribution that right. So if you know the data label is L, then the probability is 1 in the data, otherwise it is 0 for that particular data point. And then if you want to compute the cross entropy of this distribution of labels in the data, which is simply the 0 1 distribution, we can take one indicator of y equal to L multiplied by log of PL, uh, and sum and negative of this and sum over all possible limits, right? So this is the standard sort of loss which is used in deep learning, um, known as the cross entropy loss. Once again, what we are saying is that for each right, so this is for a particular data point, and then you sum over all possible data points, or average over them. But for a particular data point, what we are saying essentially, if you think about it carefully, we essentially want to maximize the probability of getting that particular label in the form of log PL, and essentially minimize the probability of all other labels. Note that in this expression, when y is not equal to L, then the indicator um, function um, essentially becomes 0, and the log PL term vanishes. So, right. So what we really care about is maximizing the probability of the label that is actually in the data, right? And our the description of the loss for this GAN network will essentially utilize this idea of cross entropy loss. Okay, so finally, let me describe the loss function for a GAN. This is given by L theta phi, right? And this is nothing but the cross entropy loss. We'll just keep the minus sign outside. And remember, the theta were the parameters of the generator, and the phi's are the parameters of the discriminator, right? And we are in a setting where the discriminator outputs its belief, or its own probability of the fact, right? Its belief that the sample actually came from the original distribution, right? So the goal of the discriminator is to maximize that probability if the data came from the original distribution, and minimize that probability if the data came from the generator, right? And of course, it doesn't know from where the data came in reality, right? It has to just look at the sample being passed to it, and then figure out the probability, right? So for the discriminator, the loss would be essentially a sum of two terms, right? So the first case would be when the actually it's a true sample, right, coming from the data, right? And we take an expectation, just to say the fact that it's sort of an expectation for over all possible samples that could be generated from the data, of the log of the probability of d phi of x, right? So d phi of x is nothing but the probability that the output that the discriminator assigns to this particular sample of it being actually from the true distribution, right? And the next term is sort of the probability mm, uh, that is assigned to samples which come uh, from let me just do this again, right? So the samples which come from the generator, right? So these are samples coming from the generator, right? And discriminator should try to assign as low of a probability to the samples as possible. Therefore, this will be 1 minus log um, or actually not 1 minus, but uh, log of 1 minus d phi of z, right? So this is sort of the total loss of this joint system, right? So once again, the first term is simply saying that if the sample comes from the data, then the discriminator should assign it a high probability, right? And right, we want to maximize that probability. And the second term says that if the sample came from the generator, then the discriminator wants to assign a low probability to that sample. Therefore, we have the corresponding terms, the first term being log of d phi of x, and the second term being the log of 1 minus d phi of z, right? And in this setting, what is the goal of the generator and the discriminator? So the goal of the discriminator, let me write that first, is simply to minimize this loss over its parameters, which are phi, L theta of phi, right? And what is the goal of the generator? The goal of the generator is to fool the discriminator. Therefore, it wants to essentially maximize this loss over its own parameters, which are given by theta, right? And this is a sort of an adversarial setting, right? And this is how it is optimized. This is sort of an alternate uh, minimization, maximization problem, and this is exactly how it is solved. So therefore, an alternate way, right, to write this would be that we want to maximize over theta parameters, and we want to minimize over phi parameters of L theta comma phi, right? And typically, the way it is solved is to alternate between this minimization and maximization problem, right? In the ideal world, you would sort of fully minimize the internal sort of expression with respect to phi, right? That is optimize the discriminator for the given generator, and then once you have done that, then you go to the generator, take maybe a graded step along theta, and then again go to phi. But this can be computationally very expensive. So typically, you don't really fully optimize the discriminator, but you do some steps, certain number of steps of discriminator optimization, then go back to generator, take a step, and then go back to discriminator, so on and so forth, right? And there are more details here, right, which I would sort of encourage you to look at the paper by Goodfellow et al. uh, from 2014, right, which is a highly cited paper, um, and probably it has more than, I think, 10,000 citations. Um, and in fact, a lot of work in today's deep learning is building around GANs for various kind of applications, both from in terms of using them for different applications and also advancing the theory of GANs. Two things that I want to mention here: there are certain problems that the original architecture sort of faced, which one of which was called the mode collapse problem, um, which is, when your input data is coming from multiple modes, what can happen is the generator can only converge to one of those modes and not worry about the second mode at all, right? And that is a problem that people have observed with GANs, and a lot of work has been around to fix this problem. The second problem that has been observed with GANs is sort of stability of training, that this alternate min-max optimization can be highly unstable, and people have also tried to address this in some of the recent works, right? And I will encourage you to look at all this literature if you are interested in knowing about this one. Uh, Before I go to sort of the last topic I want to cover today, just one minor detail that I want to mention on the previous slide is that some of you may wonder that L theta phi expression that I wrote does not have an explicit mention of theta parameters. Right, don't get confused by that. They are really hidden in the second term, where we are generating z based on gen of u, right? Generator of u, right? So these z's or z's are being generated from the generator based on the theta parameters, right? So these theta optimization over these z's, which are being generated from the generator, whose parameters are these theta parameters. Okay. So the last sort of topic that I want to talk about over today is called dropout, right? And this is also one of the very important idea in deep learning, and at the outset it may seem very counterintuitive, but it has been shown to work very, very well in practice, and has been a great idea to really help avoid overfitting in deep networks, where you could have millions and probably billions of parameters, right? So what is the basic idea? Let me draw let me um, sort of demonstrate this with the help of this small architecture, and to keep things simple, right, I will just draw this in the form of a standard sort of neural architecture, where you have um, all these kinds of cross connections, right, between units in adjacent layers, right, feeding into each other, right? And as I said, this is sort of a general sort of connected network, but in general, right, but it could be a CNN. The connections will be defined accordingly there. It could be an RNN, the connections and the weights will be accordingly defined there. It doesn't really matter, right, for understanding dropouts, right? So given this architecture, right, suppose you are training the network using SGD, right, stochastic gradient descent, right? So then what you do is essentially in each learning iteration, uh, right, of your SGD, you right, with some probability, right, let's say P drop, right, you randomly zero out some of the connections, right? So suppose there is this unit J in the network, and there is this unit maybe right. So let me just write this as this is the unit J and this is the unit K, and there is a connection from K to J, right? So what you do is with probability P drop, right, you make theta jk to be equal to 0, right? And you do this independently for all uh, jk, uh, right? So for every connection in the network, you take that connection right before each learning iteration, and with certain probability, you simply drop it out, right? And typically, this probability is different for those connections which are sort of in the hidden layers, and there is also dropout probability for randomly dropping the inputs, right? Right, what does it do, right? So in some sense, what it does is that when you're learning, when you're updating the weights for that particular iteration, the impact of xjk will be sort of nullified, right? Because the corresponding weight has become 0, therefore xjk will not play any role in really determining your output in that learning iteration, right? And some of you might say that what is the point of this? This doesn't make any sense. You are actually throwing away some of these connections with sort of a probability. And the whole idea is that with so many parameters in the network, right, that there is a high possibility that there might be a lot of overfitting is going on. And this dropping of the connection, what it does, it makes the model much more robust to essentially noise in the data or variation in the input, because what it is saying is that what is essentially statistically minimum that is required for you to produce the output, right? So it's like saying, suppose I am trying to recognize a face, and maybe some pixels are blurred, right? Or some of the internal hidden representations, hidden feature maps are blurred, right? Can I still recognize the face, right? So it's like sort of pushing you um, to the limit, in the sense that if you could do that job well, even when some of the inputs are not there, right, you will probably learn more robust, more powerful function, and this is the key idea, right? And in practice, it has been shown to give significant improvements in terms of the learned network, which has been shown to overfit to a much lesser degree. Um, uh, and right at prediction time, right, what do you do is essentially right, so at prediction time, uh, you take each of the weights in the network, and you sort of multiply the corresponding weight by the probability of it being dropped in during the learning, right? And it can be shown that the dropout idea essentially um, is equivalent under some mathematical conditions to learning an ensemble of models, right? But let's not go there. It's a sort of an advanced topic for the current class. But suffices to say that this is a very, very important idea, um, that during training you make the model more robust by randomly dropping out each of the connections independently with some probability, including the inputs, and then you learn the network in this setting, and during prediction time you multiply by the corresponding probability to the learned weights before you make the or while you make the prediction. uh, and for more details I will refer you to um, to work by Sri Vastava et al. Let me just verify uh, the name Srivastava et al. 2014 paper on dropouts, and again many variations and enhancements have been proposed of this original dropout idea, but the original idea can be found in the paper that I referred here. Um, Finally, before we break today's class, before we sort of wrap up today's class, another idea that I will not be able to describe, um, but has been very important for training of neural networks is called batch normalization, where you sort of normalize the outputs of each of these hidden layers within the network. But I will refer you to sort of relevant literature for further reading on this if you are. So one very important detail, and that I think I should have mentioned in the previous slide about dropouts, uh, which I will make a remark about, quick remark about here, is that suppose you are going from unit k to j, right? This is theta j k. So when we say that this particular connection theta j k is being dropped, right, we choose these theta jks independently in every iteration, and different learning iterations might drop different connections, right? This is the key, right? I just want to make sure that there is no confusion that there is a fixed set of connections which are dropped. That is not the case, right? So in fact, in every learning iteration you drop different connections, and that is what brings robustness, right? So in every learning iteration you go to each input, and each of the connections you randomly decide independently, with a certain probability that which need to be dropped, do that learning iteration, update the weights, go to the next learning iteration, again determine which connection need to be dropped, and proceed in this manner, right? So this is an important detail that I want to mention. Okay, thanks. I think I should stop here and we'll continue in the next class.